Okay, let me start. I'm recording this lecture and I'll upload a link to the video. This is a special class, and I'm doing this for the sake of completeness, as I could not finish the lecture, the topic of describing the bounded model checking for the whole of LTL, which has started and introduced it in the last class. What I intend to do today is to cover the remaining part of it. I'll do a quick recap of what I covered last time for your benefit, and then complete the rest of the things. The reason I felt that I had to do this was because I intend to have at least one question, a simple question on this topic in the final exam, the take-home exam. So I felt that it was only fair that I completed it and uploaded it in case you want to, any of you want to use it. Now let me share the screen. Okay, so we go to full view. Okay, as I said, bounded model checking, the way for LTL properties starts by it's by encoding whether it starts by taking the negation. Let me see if I have yeah. So it starts by converting an LTL property into its negation. Okay, and we'll assume that the negation of the property, the knot is pushed all the way inside, which you can always do. That is, it is converted into a negation normal form in which the negation appears only on atomic at the atomic level, and then it consists of showing that whether there exists a witness to violation of M. This it does not by doing full-blown LTL model checking, but rather encoding the existence of a witness, a K-long witness to the LTL property as a SAT check, and then you run that SAT check to see if there exists a K-long witness to a violation of an LTL property. Obviously, this is an incomplete way of doing it. So you will have to run the SAT check for longer and longer K until you find a witness, or you reach a K that is large enough to conclude the absence of any witness to the existence of showing violation, existence of showing that that knot of phi is satisfied, and that's what we call as completeness threshold. And in earlier in the course, you already saw how this worked for two instances, simple instances of LTL formula. The case where for invariant properties of the form G of P, where P is a predicate, and also simple Leibniz properties of the form F of P, where P is a simple predicate. In the last class, for the benefit of those that hadn't seen LTL, I introduced linear temporal logic, LTL, and its semantics of satisfaction on infinite paths. Okay. Now, that I'm going to skip today. And now this encoding of the full LTL into SAT formulas for bounded K error witness check relies on an approximation to the infinite satisfaction semantics that is usually defined for LTL. What do I mean by an approximation to an infinite satisfaction? For any given K, for any given prefix that is K long for an infinite path, I observed that the following is always true. That if for any given K long prefix of an infinite path pi, if the finite prefix of pi satisfies the LTL formula, then of course it is true for the entire path as well. But what is exploited in bounded model checking of LTL is the following fact, that if you know that if the K-long prefix is lasso shaped, if there are one or more lassos in in that K-long prefix, then it is actually possible to conclusively to conclude that that it is the property phi is satisfied for the infinite paths, the paths that are represented by such lassoing paths. That's what is leveraged to in the translation to translate the satisfaction into bounded satisfaction. Okay. Of course, as you know, that for finite state transition systems, every path that is generated by a finite state transition system must have the shape of a lasso. That is, every finite path, the only way that you can get infinite paths in a finite trace generated by a finite state transition system must be such that after you march from the initial state to up to K states, then some prefix of some suffix, I'm sorry, from L to K of this K long path must repeat itself infinitely. Okay, and that's the only way that, I mean, all infinite paths on a finite state transition system has to have this kind of a structure. And that follows from the fact that for finite state system, every infinite path must be an omega, it must be representable as a omega regular expression. And this is the one that is leveraged. Okay. And we saw briefly in the last class how this aspect was actually leveraged to define a bounded semantics. That is, what it means for a finite path, what we can conclude by inspecting a finite prefix of an infinite path. What we can infer about satisfaction of an infinite path using only a finite prefix, K-long prefix of that infinite path. Okay, and I'll start by visiting that thing again. Okay. Before that, let me show you a few examples of how lassoing, how one could encode whether a k-long finite path has a lasso shape or not. Okay, as I said, so an infinite path of a finite state system has to be of this form. So such a path can always be represented as some sequence as a SAT instance of this BMC, bounded model checking formula, where the first part between square brackets denotes a k-long run of the transition system from an initial state S0 to Sk. And then if it is, we say that it represents a KL lasso if the state Sk folds back into a state S that occurs at index SL, the index SL that has already appeared in the prefix earlier, which can be checked by checking if the K plus first state produced by the transition relation is equal to SL. So, that's how it is checked. Now, a set of K lasso paths represented by K long prefix BMC can be now represented by this SAT formula, where you check if there are several lassos, if there are several positions where the Sk state lassos, by checking if the K plus 1 state, that is the successor of Sk, is equal to any one of the states starting from S0 to Sk. Okay, if it loops back into any one of the states, and that is represented by this disjunction in here. Okay, so this satisfying instance of it just represents a set of parts, set of all lassos. I'm going to go quickly to this example. For example, here in TS1, there can be no 0, lasso, but there is a single 1 lasso represented as S1 followed by S1 omega, which is appears as is exactly characterized by the satisfying instance of this formula. Okay, so this is a 1 lasso because you go from T0 to T1 and then the successor of T1 lassos back. Similarly, the set of all 2-1 lassos in the transition system TS1 are represented by these two omega regular expressions, S0 followed by S1, S2 omega, and S0 followed by S1, S1 omega, which are characterized by the set of all satisfying instance of this formula. That is, you go from T0 and go till T2, that is too long K path, and then check if the successors of T2 are any one of the states that appear in the predecessors of T2. Okay, and in this case, there are two possibilities, and this kind of encoding is encoded. Is leveraged, is used in our translation of the BMC bounded model checking formulas for checking the violation of for entire LTL. Okay, so now I'm going to be defining the bounded semantics for an LTL formula. Okay, that is describing in these rules, describe given a path pi. Okay, there are two kinds of translation. Here I'm going to be defining a formal bounded semantics of the loop. That is, if you're given a finite prefix, k-long prefix, of an infinite path of a finite state transition system, how you could define, how you could infer from the satisfaction of the LTL formula by looking at the finite k prefix, what if you could conclude, what you can conclude about the satisfaction of the infinite path represented by the KL, one of the infinite paths represented by the KL lasso. So it is defined, since we are defining it for an arbitrary LTL formula, just like infinite semantics of LTL is defined recursively, here also it is defined recursively, except that there is one set of semantic rules for the case where the k-long prefix is a lassoing path, and another definition of bounded semantics for the case where the prefix, there's no lasso there's no lasso exists for in the k-long prefix. Now this one is bounded semantics for the looping, when the prefix is looping. So yeah, you start with the simplest atomic predicate of LTL, which is just a predicate. And here, by the way, the satisfaction relation, since we have to look at the formula can have nested temporal operators. So, we define what this notation, pi satisfying ik of an arbitrary LTL formula, what it denotes is, it denotes the satisfaction, it denotes the k, the suffix of the path k-long prefix of path pi, starting from the ith location of that k-long prefix. Okay, and then you'll see that we will instantiate this for defining with I instantiated to 0. Okay, so you should read it that way. Okay, pi from I to k. So how can you infer? What can you infer about the satisfaction of a predicate? If P is satisfied in the by the path infinite path pi, if in this case you can precisely conclude if the predicate P is satisfied by the state in pi that occurs at I. Okay, so you can precisely capture it using by just looking at the k-long prefix. Similarly, for not P, the P has to be false, has to be not satisfied by the state at pi. And if there are two, conjunction of two things, then you apply these things for both sides, both of the conjuncts. Now it gets interesting when you have temporal operators. Here I'm defining the bounded semantics for the looping case for the next state temporal operator, the G for ever operator, and F. Later on, in a slide, I quickly indicate how it can be done for the until operator as well. So here we are defining what we can conclude about the satisfaction of a formula, of an LTL formula of the form X of F, where the subformula F itself can be an arbitrary LTL formula, by looking at the suffix starting from the location I in a k-long prefix of pi. Okay, so that is what this thing is defining. So, and you will see that we are going to be exploiting that you can actually conclude, you can conclusively show the satisfaction for the infinite path that is represented by this lassoing path. So X of F, if I is equal to if you're at the end, if I is equal to k, then you know that since you know that this is lassoing, the successor of sk is sl, and x of f is true only if the formula is true of the state which is a successor of sk. Now, in this case, since it is looping, you know that the path, the path is lassoing into a state in SL. You can conclude that if you're at the end, then all you need to do is to check if f is true of this suffix starting from suffix of the k-long path starting from SL. And that's what it is defined. That is for the case when I is equal to k. But if I occurs in the tail part of it, anyway, between S naught and, the tail between S naught and SK minus 1, then all you need to do is to check if F is true of the next state, because that is by you can get that by checking for Si plus 1, the state that occurs at the I plus 1 index. Okay, and that's how I hope you get the idea that how you could leverage the fact that that the k-long prefix is a lassoing path can be used to determine precisely and completely the satisfaction on the infinite path represented by the k-long prefix as per our convention. Okay, so let's see how you could what you can do to define for G. Okay. And for G of F, it is true if you, all you have to do is to check if your, if I is anywhere, it's less than L, then you will have to check that G is true for all states starting from I till SK. Because once you check it is true for the part which is inside the looping part, and since the infinite path, is an infinite repetition of the states from SL to SK, you know that it'll be true for all the states in the infinite path. And that's what is being checked. So what you need to do is to check if it is true, if F is true of all the paths starting from the min of I of L. Similarly, for, if the formula is F of F, then you do, you'll have to check if F is true in any one of these states that appear between S1 and SK, okay? Because if it is true earlier, then you know it is true for the infinite path. And if it is true in any one of these, states, you already know that it is true for the infinite path as well, because the infinite path is just a repetition of the SL through SK. So you can see that if it's a lassoing path, you can completely and precisely extend the check. You can extend to conclude completely and precisely satisfaction for the infinite path by just looking at the k-long prefix. Where you get, now I'm going to describe the semantics, the bounded semantics for when the k-long prefix of the infinite path does not have any lasso at all. Okay, that is So that is the successor. That is in this case, successor of SK is not doesn't appear anywhere. Is not equal to any of the states from S naught to SK, including SK. So here you will see that in some cases, for some temporal operator, you won't be able to precisely characterize the satisfaction. You'll be precisely able to conclude from the bounded satisfaction anything about satisfaction of that LTL formula on the infinite path, which can be an extension of the k-long prefix. Now let's see. For the case where P, it's a predicate P and not P, then of course you can check if it is true at that location. Then obviously it is true for the infinite path, which is an extension of the k-long prefix. Let's look at the temporal case. The question is, if it is x of f, if you're at the end of the k-long prefix, since you don't know if that k-long path is, since there is no lasso, so you don't know what the next state is, because x of f is true only if f is true of the next state, starting from the prefix that goes from I to k. If I is equal to k, since you don't know the successor, you can't conclude anything from it. And that's why we return false. That's what I mean by this bounded semantics approximates the path. So in this case, you cannot conclude anything about the infinite case. But if I is less than k, then of course the successor state is inside the k-long prefix, and therefore you can just check if f is true of the trace, which is a suffix of the k-long prefix starting from I plus 1, whether f, the nested LTL formula, is true of that. And that's what is done here. Now, let's look at for the G case. Okay, for the G of f case, since this is true of an infinite path only if f is true in every state. I mean, for every suffix starting from I. Okay. So since we don't know any that it is lassoing, since it's not lasso, we know that it is not lassoing. So we only have a k prefix, and therefore there's nothing you can conclude about the infinite path by checking only for the finite k. And therefore, you cannot conclude anything even after checking if f is true in for every prefix starting from I of the k-long prefix, and that's why we assign false. Whereas for the f of f case, here also sometimes you can conclude precisely and sometimes you cannot, if by looking at the suffix of the k-long prefix starting from I. So what you have to do is you'll have to check if f is satisfied by all the suffixes starting from I. All the suffixes of the k-long prefix starting from I till the end. If it happens, that's why I'm taking a disjunction of those satisfying formula. And if it is true any one of them, then of course you can conclude. But if it is not true, of any one of them, then it'll be false. This will return false, and therefore, because in that case you cannot conclude anything about the infinite path pi, whether eventually f, if there is a point at which f holds true. So you can see that the bounded semantics for k-long prefixes, finite paths that don't lasso, is an incomplete semantics. So how do you then, so given this semantics, the question is, how do you translate? How do you, how can you come up with a general schema to translate existence of a whether given whether you can conclude existence of a satisfying path, infinite path for an LTL formula, okay, expressed in an NNF form, by looking at only the k-long prefix of that infinite path. Obviously, we have two translations based on the semantics that we just now saw. For the case where the K-long prefix has one or more lassoing is a lassoing. I mean, it has one or more KL lassos for different Ls, or the case where the K-long prefix has no lassoing paths at all. Okay, that is the case. Yeah, in the first case, it represents the K-long prefix represents a set of infinite paths for which you can, get a precise translation. So how does the translation at the top level look? As always, in bounded model checking, there is a part that characterizes the fact that the S naught through SK is a K-long legitimate prefix of an execution of a trace starting from an initial state that is represented by this BMC formula. Okay, where success, it starts from the initial state satisfies the starting state S naught satisfies the initial predicate, and two successive states in the sequence, any two successive states is related by the transition relation. And to this, we add a looping to characterize the looping case. We add a loop K, which is a constraint which characterizes the fact that there is a KL lasso. That is, that there is it loops back into position, the K successor of SK, the last state in the K-long prefix, loops back into the state indexed at L. And that's what this loop K of L satisfies. Now, add that there is a K to L lasso in that K-long prefix. Now, the other case is when the K-long prefix contains no lassos at all. That can be represented by this disjunctive formula, which says that that there is the successor state of SK, that it does not loop into any position starting from S naught to SK, that there is no lassos loop lassoing to any position starting from 0 to K, and that's how it is represented. Therefore, what we have is the complete translation of that leverages the bounded semantics definition of translating an LTL formula into a BMC formula is as follows. Here, K is this notation. K is any given transition system, a Kripke structure with predicate labels for all states, and an LTL formula which can have arbitrarily finite sized LTL formula F, which can have arbitrary nesting of temporal operators. So far, we have considered only unary temporal operators. Okay, so given that, so what it has is, if there is no loop at all, then you have this notation denotes the no loop translation. You're going to see how exactly the translation into a SAT instance is done. So for now, I'm saying this is a representation of F within square brackets 0K, represents the SAT translation of the LTL formula. Okay, so since you have to look at the entire K-long prefix, you start from 0. The other case is for where the K-long prefix can have one or more lassos in it, as we saw in the examples earlier, in which case you will have to, it can, the successor of the kth state in the k-long prefix can lasso into any one of the states from 0 to k inclusive. And therefore, you have to account for, to generate one translation for every possible way in which you can lasso for every L. Okay, that's what this represents. Okay, so for L, start iterating from 0 to K, then you have to generate. So this is actually what it is: a disjunction of a conjunction of formulas, where each conjunct represents a case for one lassoing, one lasso for LK, where L can range from 0 to K. So this is a nested formula. We'll see an example. I hope you understand. So this together represents, if there is any satisfying instance, this captures the satisfaction case both for looping as well as non-looping case. Okay. I'm sorry. Yes. This is at the top level. Now, we will see what the translation, that is, I'm going to be defining this one, square bracket, the non-looping translation, how exactly it is done. You will, based on the bounded semantics that we defined earlier, and this LF0K, which is the translation for the looping case. So first I'll describe non-looping translation. Okay. So if you have, if your LTL formula is just a simple predicate, then your translation, that is a SAT translation, that is the first order formula that you have to get, that you have to translate this thing into, is just checking if the predicate P holds of the state that is indexed at I in the K-long prefix. So it's a simple atomic predicate check. Similarly, not P is checked by the negation of P, and if it's a conjunction, then you recursively check if F and G holds good. So let's start with the interesting case of the temporal the cases. So if you have a formula where the topmost temporal operator is X and the subformula F is an arbitrary LTL formula, to translate the check of if infinite path starting with the suffix I satisfies this by looking at only a K-long prefix is as follows. So you just check, because in this case, as long as I is less than K, all you need to do is to check if F is true for the successor, to the state at I plus 1, that's at I plus 1, and that requires you to recursively apply the translation schema that we are defining to generate the translation. So this is a nested translation. Okay, so I'm recursively invoking the translating operator on the nested subformula F on the prefix, on the suffix of the K-long prefix starting from I plus 1. Now, if I is greater than or equal to, if I is greater than or equal to K, obviously you can't conclude anything, because that's what how the bounded semantics, as you saw before, said, and therefore you just translate it into false. For G, since the translation, bounded semantics translation is false, you can't conclude anything, so its translation is simple, it's just false. And if it is of the form, the temporal form is of F, then all you do is you will have a disjunction of recursive translations. Okay, and to check if you have to generate formulas, SAT formulas, to check if the subformula F is true of by looking at the prefix at one of the suffixes starting from I of the prefix k-long prefix, and that's what this thing is. So you are invoking here recursively the translation operator for k times. Okay, for each is j starting from I to k, and that's what you are taking a disjunction of. This is exactly how you look at the bounded semantics, and you can come up with this translation scheme. Okay. Now, the looping translation also follows pretty much the pattern as defined by the looping translation, by the looping, the bounded semantics definition of for the looping case. So, all the first three cases remain the same. Now, here with X, yeah, as you saw, this denotation for the translation operator has an L here because you're to denote that translation is for the case where the k-long prefix of an infinite path indeed has one or has at least one lasso. Okay. Yeah. So if you're translating X of F, what you need to do is to recursively apply the translating operator for suffixes, for every suffix in the k-long prefix, starting from starting from I. Only difference is that's what nextify does. So where nextify is defined this way. So when you get to the end of the k-long prefix, since you know that it is looping, then in this case, you can actually replace that with next of I will be I. You know that it is I plus. Uh, if it is less than k, then you can actually increment I. If it is not, that is, I'm sorry. I mean, if it is, if you're at the end of the k-long prefix, since you know that it is lassoing, then your next thing has to wrap around to L, and that's how you translate. So GFF of translation is conjunction, since you have to check. For every position which is suffix of the k-long path, which is a prefix of the infinite path, starting from the minimum of I of L. So you will once again recursively invoke this operator so many times, starting as many times as starting from the minimum of L of I to K. And in the case of F of F, it will be a disjunction. Okay. So I only have 10 minutes, before I have to catch the thing. So what I will do is, so this is, so as I said, the translation for the general translation will have two components, a disjunction. One for the no loop case, in which case you will apply this translation f of 0 of k, and that is a recursive translation, like I showed you, in the last couple of slides. And for the looping case, it will be a disjunction, a disjunction with one disjunct representing the translation for the pause, the case where the k-long prefix can be lassoing into L, where L can be an index anywhere between 0 to the last index of the k-long prefix. And the main theorem, which says is that, a case, for a general thing, for an infinite path of on any k-long, a key model represented by k satisfies, this existential F formula, that given any LTL formula, if there exists some k for which this thing is satisfiable. Okay. So the interesting fact is, I'll only show for the if the temporal operator, the thing is the translation are linear in the size of k. Okay. If some formulas are all unary operators, provided you use some sharing, And if it has binary temporal operators like are and until operator, then the translation is quadratic. So it's a fairly compact translation. The SAT formula that you will have to check is a fairly compact translation. Of course, it grows as the size of K grows because you have to have K corpus. Now, this slide has a translation for U and R, and I don't have time to cover that. So I'll show you in an example how exactly the translation, the invocation, the recursive definition of the translation scheme I showed in these two slides here and here, where this slide puts the whole thing together, works on a actual example, and I'll end after that. Okay. So I'm illustrating here for this particular transition system, which has only, a single lasso, an infinite path, which is, of the form S naught followed by S1, S2, S3, omega. Okay, that's every infinite path has that shape, and therefore it has, if you look at the K3 long prefix, that's the lasso path. Anything less than 3 long prefix of these infinite paths generated by this transition system is not a lassoing path. So if you want to check, do bounded model checking of this nested LTL formula, which has a 3-level nesting of, you're doing G of F of G of P. That is, you're checking that on every trace here, eventually you get into, whether you will get into a point where the predicate P, here P is a predicate, okay, consistently forever satisfies, P. So, for example, that is true here if any, if the states S1, S2, S3 satisfy, all of them satisfy P, because S naught may or may not satisfy P. But here in this case, you will eventually get to a point where every state will satisfy. Eventually, you will get to a point where P is consistently true. So the translation will start with starting with the K long. I mean, I'm assuming that I'm given the translation for 3 long prefix. Then, so you will start with whether you first check if it is here. This is a graph where the solid edges represent and, conjunction, and dotted edges or. And you can see it has recursive invocation of this L of the square brackets starting from 0 to 3. And then that will be recursively invoking 0 to 3, 1 to 3, 2 to 3, and 3 to 3, which in turn, for every sub-formula of this G of F of G of P. Okay, the first level is invocation on the entire formula, the LTL formula. The second layer is the recursive invocation of the translation operator for the sub-formulas, okay, at the next level, that is F of G of P, okay? And there'll be, depending upon what the temporal operator is, there'll be either a conjunction or a disjunction. G will translate into conjunction of subformulas. F will translate into disjunctions. And you will go down the subformulas in the LTL formula. And that's how you generate, which finally ends, the base case will be when you have the predicate P, which gets translated into checking P if it is true for any one of those states. What I've shown here is, of course, this is a branching thing. I mean, it's a tree. Therefore, if you don't use sharing, then you can have kind of an exponential blow up. But if you represent it as a graph and you share sub-isomorphic subgraphs, then it will be a linear translation. And I hope this will give you some idea of how the translation works. And I encourage you to review this talk and the slide to work through this example by looking at on this translation, okay, for this thing, and see how you can, what exactly when you expand this formula, it'll turn out to be, okay. Or you may choose a smaller formula with at least two temporal operator to get hang of it, okay. So that's what I'm doing, and I'll since I've covered this and I've taken the trouble to cover it and then have the thing, so I feel obliged to have at least one simple example in the simple problem in the take-home final exam. You can expect that. And what I will do is please keep a watch on my messages that I'll be posting on the WhatsApp group, or that I could be sending through email through my emails on Moodle about the take home and exams, what the structure of the exam is and what the problem is, and about the dates and so on. And watch out for that. And I'll also announce the dates for submission of the project, as well as the dates for the final exam. Keep a watch on that. And I'll be available for the whole of next week on demand, for the whole of this week on demand, to discuss with any team about the project. Please send me an email. And if you have any problems and issues in either developing a model or doing the proofs, I'm willing to help you out. Okay, so best of wishes for all of you, and that's it. Good luck and goodbye.
Thank you.
Thank you.